Hello, Alice Sage here. Today I want to talk about my methodology of vulnerability research, especially how I managed to find zero days and write exploits for across a variety of highly complex and hardened software like browsers and hypervisors. I have my notes here that I will be using. There are 10 points. There are 10 points, and I think that this methodology is very universal. It can be applied to pretty much any research area where there is complexity, uncertainty, and the requirement to push the boundary to develop novelty. Probably in much of scientific research, the same system would be used, so it's pretty much universal. Point number 1, I build systems. Systematic approach is the core of my method. It's not something that I strive for, it's something that just works out for me naturally, not always intentionally. The systems can be of different types. They can be mental, physical, technical. In my work, I use all types of systems. Generally, I lean towards mental systems a lot that actually govern how things work in what I do and what I want to accomplish. And they are the most powerful, I think. I'm a business owner, so I have business systems in place. Operation, strategy, various things. I have R&D, which builds on its own set of systems. I have productivity that covers everything. That's a top-level overview of different types of systems that I'm using. In vulnerability research specifically, I use abstract models. I use systems for automating specific concrete technical tasks. And most importantly, I use systematic approach when I study new systems that I want to research. Last year I made a video on how to analyze complex systems. It went viral for a good reason. The skill that I was showing, it kind of looked simple, but it's very foundational and important. I was showing how to kind of a recursive approach to breaking down a system to separate it into subsystems. Recursive is the keyword here. Here, when building systems, I use exactly the same skill in the other way around. So I build a system recursively, and the system that I have, like you have a mission, for example, then you have some big systems to support it, to accomplish it. If you zoom in, there are smaller systems inside it, and this process can go on indefinitely. So it's a recursive generative process. Point number 2, I reverse engineer tons of case studies. In my area, that would be vulnerabilities. I look back at 10 years ago and more if available. I study all the bugs that I can find. This gives many advantages that most people underestimate. One big advantage is instant visibility into available attack vectors and architectural aspects, various aspects of the implementation of the target software. Another aspect of it is bug patterns. Bug patterns recur more often and broader than most people think. Patterns from 10 years ago and 20 years ago tend to recur in newer systems, in different other subsystems. It just happens all the time. Point 3, using abstract thinking. Security research is concrete, so we work with specific code, we need to work with a debugger. It's as concrete as it gets. However, many people confuse this concreteness with for everything that it is. In fact, this concrete level is just the top level of the trade, and then beneath it is many levels of abstractions that hold the real power regardless of what you're doing. There is a couple of ways how abstract thinking applies. There is many ways how abstract thinking applies to vulnerability research. The most obvious, I think, number 1 is building abstract models for whatever you're looking at. That would be models of the concrete implementation or class, models of bugs, of exploits, and another one is the abstract model of the vulnerability. the abstract model of vulnerability is something that remains when you abstract away concrete details and focus on the core of the bug. Usually you can derive this kind of abstract model by looking at multiple different vulnerabilities and kind of matching it in your mind in such a way that surplus can be thrown out and you just get this core. And this core has the interesting property that it has a big transfer radius. It's no longer constrained to a specific subsystem or a specific implementation. It can be moved across different implementations, subsystems, across time, across space. You learn once and then you just apply it across the board. That's the power of abstract thinking, and I feel like many people in my industry underestimated it wildly. There is another huge benefit to abstract thinking that I will mention a bit later. For now, I'm moving on to point 4, which is I create attack surface models. Attack surface model is a specific subset of an abstract model that I build. It's a graphical visualization, highly hierarchical, detailed representation of the architecture of the target class with the offensive perspective in mind. So it reflects what would be reachable for the attacker and what is meaningful for any sort of boundary violation. I build abstract models of class, not of a specific implementation. So for example, I looked at hypervisors, and I have this singular model of hypervisor attack surface model, which reflects attack surfaces that exist in pretty much any hypervisor that exists today. The attack surface models are hard to produce. They don't exist out there as something that can be copied or read up in a textbook. You have to reverse engineer it. I built it from studying a lot of vulnerabilities, like hundreds of vulnerabilities reverse engineered, plenty of specifications read, technical documentation. You consume all that information and you build this model. It was quite surprising. I think in 2018, I was researching hypervisors and I looked at several hypervisors in a sequence. Studied the system internal, studied vulnerabilities, VirtualBox, Hyper-V, VMware Workstation, ESXi, and KVM. And once I was looking at these different implementations, I noticed something remarkable. They all share the same abstract model of attack surfaces and the model of what you can attack, basically. The attack surfaces, vectors, patterns, all that. And that was extremely surprising because Hypervisor is not the type of software that has a specification laid out somewhere out there. There is no predefined document that defines how a hypervisor is structured, what is its architecture, what is its implementation. The entire industry of hypervisors and virtualization grew up organically, governed, or better say, steered by a handful of foundational papers, occasional papers dropped by active developers like VMware that focused on implementation details. It grew organically, it built itself up ad hoc. So, which was the reason why it was so surprising that all of this software had the same abstract model behind. It doesn't make sense at first. Currently, I have a very good understanding of where do this abstract model come from and why does it work like that. It's a very amazing process. Obviously, for some types of software like JavaScript engines, the specifications are out there, but once again, the specification that is out there doesn't cover, for example, implementation details. It just covers functionality, what is expected generally of the engine, but it does not cover how exactly it would be implemented. It does not cover at all anything related to JavaScript engine optimization, for example, how it works. That is completely gray area where vendors play whatever they want and implementations differ a lot. So when you have this kind of abstract model, it is extremely powerful strategic instrument when looking at any kind of implementation of that same class. It shows you where the implementations would be similar, have the same attack vectors, attack surfaces, and then also it highlights where the implementations would be different. The attack surface of a class shows what is in common, and then every implementation will have also its own peculiarities. Both obviously are very useful for discovering zero days, writing exploits, doing any sort of security research and hardening. So the purpose of abstracts of attack surface models is clarity, supporting novelty. Basically, it has a huge predictive power. And we know that in all kind of business and research, predictive power is probably the most important thing that sets apart the one player from the other. Point number 5, I set expectations. Before approaching any system that I want to work with, I spend some time studying its system internals, vulnerabilities, like I mentioned before, anything that I can find, with a very specific purpose to set expectations of what kinds of bugs, what kind of attack vectors, bug patterns I will find. This is essential because generic tools can only go so far. When you don't know what you're looking for, you think you can run a fuzzer, it finds some bugs, and you have no idea how many more bugs it has missed, because that particular fuzzer approach did not cover a specific type of vulnerability, which happens to be the most interesting in that part, in this specific software, for example. So part of the information source for building this kind of expectations, as I said, is all sorts of documentation and vulnerabilities. But then also there is another interesting aspect of it, which is the hardening process itself. So every modern system is exposed to an adversarial environment where it has attackers who find vulnerabilities, defenders who patch them, usually devs themselves. This process goes on and on indefinitely. It has a few interesting aspects, properties. One interesting property is that it's not uniform. Another one, it's not shallow. And the third one is it leaves a breadcrumb trail, which allows you to understand at which particular state the software is in any given time. I built a separate model for that. I have been talking about it for a while in presentations and in my courses. Based on what kinds of and types of bugs being discovered right now in software, what kinds of subsystems are exposed, you can make a very solid judgment on what type of vulnerability is most likely to be found currently, what class, what type of pattern, without even looking at implementation or architectural details. It's like a quick heuristic that takes literally 5 minutes. You can open the CVE lists, you can read. Actually, CVE lists is a bad example because nowadays they barely even publish any details. It's very generic. Anyway, if you have the source of vulnerabilities in the software with information about the bug pattern, subsystem, more technical information, just looking at it, 1 minute gives me a solid estimate of a huge amount of information of where this particular software is at in this hardening process. Will it be easy to attack it? What specific tools will work? What attack vectors are more likely to work out? What bug patterns should I optimize for? If you don't optimize your tools to a specific bug pattern, then it's likely not working at all. Obviously, this is more important for the hardened type of software that I work with. Like you probably can't expect to approach a hardened browser like Chromium and find some buffer overflow out of the box. Although it happens. It happens. So this is a strategic tool that gives you an universality instead of depending on luck or whatever happens. Point number 6, I invest into setting up an R&D platform. The common beginner's mistake when they start finding vulnerabilities is approach the process head on. Because why not? The open source code is out there on the internet. You can open it, you can put AI to the code base, find the bug immediately, and then you have that software installed on the same system. You can test it, right? No, it doesn't work like that. I mean, it can, but it's unreliable. Some kind of bugs won't even manifest like that. For example, if you have a buffer overflow with very small margin of override, in most software the memory is more contiguous than you would expect. So if you have a very small margin of override, it will likely just override some random memory, something useless, not never used, and it will never crash. So you will be testing your bug, not getting any results, breaking your head about why is this not happening, and the reason is that you were using the incorrect research platform for that. In this specific scenario, you would need to use either an instrumented binary, which usually is not available for download, so you have to build it yourself, or just a normal self-build. To avoid this problem, when I approach a new system, I set aside a certain amount of time to set up a proper research platform that has everything I need, all the configurations, all the debuggers, all the sources, cross-referencers, and so on. It takes about, for most modern mature software, it takes maybe a couple of days, assuming prior exposure to operating system, building software, Linux command line, and so on. So for most that's a few days. For something more difficult, maybe up to 1 week. In very rare cases, when the system doesn't have a certain element, essential element of the research process, like a debugger, then you may need to set aside more time. So I personally would do it. If I have a system, like I was working with the Hexagon reverse engineering and look at vulnerabilities in the baseband of Qualcomm. It's a very hardened system. It doesn't have a debugger, like at all. In Microsoft, we have Windows debugger. In Linux, we have GDB. On Mac, we have LLDB. In Hexagon, there is none. And so the first thing I would do is to set up a platform and develop a debugger for it. In this kind of situation, it will take 1 month or more. But that's an extreme case, and for most situations, it's not even relevant. It's just good to understand that you have this capability, and you just can't build something that is missing if you need it. So the setup of the R&D platform. You need an IDE with code, with cross-reference or something like ClangD or IntelliSense. A self-build is non-negotiable. If that's an open source software, you build it, you get debug information, additional symbols, you get full stack traces, you can set breakpoints. The setup to attach the CPU debugger, which is essential. The setup of fuzzing, kind of optional, but also good to at least to understand how it works with a specific software. Various program analysis tools, for example, I would need a CodeQL. I would build a CodeQL database for the codebase, and so on. The most essential is the IDE with code, with proper referencing, the self-build, and debugger setup. And then also additional scripts with command line arguments that set a specific configurations so that you don't have to look it up every time. The point is, if you don't have an R&D platform, you get this kind of, it doesn't feel like friction, it feels like annoying blockages, right? You have a flow when you're doing the research, and this kind of blockages, they just break all the dopamine balance and completely ruin the productivity. Point number 7, I use all the tools, but only the foundational ones. I do not usually invest my time into investigating and trying out every single script, every single app, every single useful piece of software for reverse engineering. Rather, so most of these tools actually build up on a very compact set of foundational software tools that actually make sense to study, which is what I do. Things like core debuggers, like I already mentioned, GDB, Windows debugger, LLDB, and then Python. The Linux command line environment is excellent for setting up all sorts of fuzzing things and code analysis. Now, in vulnerability research specifically, historically there were 2 specialized classes of tooling: the fuzzing and program analysis. each vector with its own tools. Recently, AI was added to that stack, and for me, it clicked into my stack and into my systems very nicely. What I see is that for many people, AI has blown out their entire methodology, and they're currently figuring out how to rebuild it. For me, it was the opposite. It clicked inside my systems, and it gives me a boost on the processes that I have been applying before that, and I will be applying for as long as they work. I use the same process. AI accelerates it, increases the scope, increases the level of details, takes off the loads of routine intellectual processing. Now, as I mentioned, many people now, many researchers are kind of uncertain about where is this going with the AI tools. Some are afraid that AI will replace them. Let me be honest here. AI will absolutely replace you if you're using shallow approach. So if you imagine the distribution of specialists like kind of pyramid, at the bottom there is a huge amount of shallow specialists that apply highly patterned approach, script kiddist types. Then the middle is more advanced kind of people that understand what they're doing, understand the core methodology of how the tools work and so on. And then there is the top who strive to think as deeper as possible and develop custom their own novel implementations and so on. What AI is doing currently, it will wipe this bottom shallow fraction completely. It squeezes the middle part very hard, and the top part of this pyramid gets a boost, which is where you want to be. And specialists in this top part of the pyramid also become irreplaceable. Point 8, I optimize for novelty. I avoid highly publicized attack vectors, bug patterns. For me, it's not so much about avoiding something popular, but rather building a more strategic approach to what I do. So I lean into discovering novel attack vectors, novel methodologies, and bug classes, rather than what most people do is getting inspired from a blog, taking attack vector, looking into it, finding another bug in it. This is shallow. This approach, optimizing for novelty, compounds. Shallow approach doesn't. And it builds depth that gives a certain immunity from AI. When you optimize for novelty, that is exactly where the AI is going currently. It's squeezing that entire pyramid of common knowledge and pushing the industry towards the margin where there is no common knowledge that AI could learn from. So everybody has to go there. For me, I have been doing this like 10 years because I was optimizing for novelty and depth and abstract thinking, abstract modeling for 10 years. I am already at this point where the AI is driving everybody else. And for me, I look back and AI clicked into my system. I just use it as a fantastic tool. Point 9, I regulate my central nervous system and my biochemistry. This is super massive in this particular area that I'm working on. It messes with your biochemistry very badly, with neurochemistry in the first place. Then it goes down to biochemistry and the body, the nervous system at large. Human body wasn't built for solving this kind of problems and dealing with all this complexity. It keeps hitting bottlenecks when you do that. In the past few years, I studied a huge amount of information about how biochemistry works in the human body, how nervous system works, in order to regulate that. The common approach here is people using various substances and supplements to manage it, but what it really does, like if you're using a supplement, you're just throwing some energy into the system. If the system is operating incorrectly somewhere or already overloaded and you're blocking the signal of overload and keep adding energy, what happens is it's not just the burnout, it can be quite much worse. It works on a short term, but it accumulates the damage. And so in a few years, you get to pay. which is why I have a lot of sensitivity, and so I was able to track down these processes early before they ruined my career and burned me out, and I started regulating them. I'm going to give you one example. Everybody nowadays is talking about dopamine and serotonin, but setting aside the dopamine, which is kind of mainstream, not many people know about adenosine. When doing high complexity work, the intellect consumes ATP at high rates in order to be productive, to use the neurons. ATP is the main currency of the body, and when ATP is consumed in the chemical reaction, the byproduct is adenosine. Adenosine, there is several aspects of it that most people are not aware of. One aspect is that when doing high complexity intellectual work, the rate of clearance of adenosine is lower than the rate of its production. So it accumulates. When adenosine accumulates, it acts as a hard fuse on the brain work. So you get cognitive fog, you get fatigue, you get tiredness. Basically, the brain refuses to work. And it's a normal mechanism which protects the brain from metabolic stress and potential damage. When doing high complexity work, adenosine accumulates. What most people do is use caffeine, which blocks adenosine receptors. It blocks receptors, but it doesn't clear the molecule. So adenosine keeps building up behind the wall, and once caffeine goes out, it hits all the receptors at once. Over time, so obviously this is a problem in itself when you get this avalanche of fatigue, but also over time, when you get this situation, it creates a certain effect on the adenosine receptors themselves, and dysregulates the entire system of how the brain regulates its metabolism and productivity. Another aspect of adenosine that many people don't know is it clears during the sleep, and it uses certain chemical compounds to bind with when it clears. Which means, if you're not getting enough sleep, 7-8 hours, adenosine cannot be cleared out, you wake up tired. Which also means, if you're doing this kind of high complexity vulnerability research work, one night may be physically not enough. It depends on, obviously, personal physiology and biology, but in general, it accumulates so much adenosine that it cannot be cleared in one night. So you will have the outcome, engineering a schedule that has additional weekends in the middle of the week, for example. This also means, as I mentioned, it uses certain compounds like magnesium. If you're doing vulnerability research work or whatever, high complexity intellectual work, and you're doing everything right, not too much caffeine, don't block it, sleep enough, you still have another bottleneck, which is this process consumes magnesium very fast, so you need to supplement it. Taking it from food is not enough in this situation. So this alone, what I explained here is one specific biochemical mechanism, not even going into details. And just understanding that mechanical core of it already allows us to understand a bunch of phenomena that happens in real life, understand the phenomena, build several solutions that genuinely solve it without ruining the system long term. And it's all actionable, right? You can literally start doing it today. Point number 10, I set boundaries, project boundaries, time boundaries, scope, what I will look at, what I won't look at. I set timers for each task. I set containers, time containers and scope containers for each project. 1 week, 1 month, everything is bounded. There is no open-ended process. Why? Because in this type of research, the amount of uncertainty that exists here, it will just consume your brain and your entire energy if you don't contain it. How to contain it, how exactly to set it, this is a separate topic. So for example, at some point I was using a very simple principle. When I'm starting to research new software, I give myself 1 month to find a 0 day in it. That's completely from scratch, without prior knowledge. And it was enough, it worked out. That was before the AI era, nowadays maybe a bit faster. Now the beautiful thing about it, the boundaries are dynamic. You have to mutate them as well. So after doing this project for a month, for example, I know that for the next bug I need 1 week because I already have the foundation built.